This is Geometry, Semester 1. It's the unit Rigid Motions, number 6, and it's the Lesson 5 on Dilations practice. And in all fairness, dilations is not a rigid motion, but we drop it into this unit nonetheless, and I'll explain more about that as we go. This is on creatormath.com under the Geometry tab. You might have to Google creatormath.weebly.com to find the site. The instructions are copy the following problems into your composition book on the correct pages according to the table of contents with the notes for those pages from creatormath.com. So let's go ahead and take a look at that. This is the website here, creatormath.weebly.com. That's what you should Google. Hopefully you can get to this home page. So under this home page is all the information on how to put your composition book together. Just find the large print composition book, follow all these directions, watch all these videos, and do the work, and you should have a 90 to 100% on your composition book. Now we're going to go find notes and problem sets and vocabulary for geometry. That's all under the Geometry tab. This is the Vocabulary Geometry Practice Study PDF. Every single word we use for the entire year is on this PDF, and I don't mean necessarily English word, I guess I mean geometry related words, right? And it's like 420 of them or something, but they're all there. That document is searchable as a PDF. Google how do I search a PDF with the device you're on to find it. If you don't have 100% on your vocabulary practices, then you may not know how to find that PDF yet. All right, so try to figure that out. We're going to go to the semester for this video. This is semester 1. This is the table of contents. You should have already copied this entire table of contents on the pages 2 through 6 of your composition book. If you haven't done that already, please stop and do so now. We are going to find the rigid motions unit. There it is. So here's rigid motions. Dilations is down here at 5, and here are the pages where the notes go, pages 115 through 116. Notes, problems, and the video solution will be here. Don't follow the page numbers from this video. Please look it up again at the time you're watching this video. The page numbers probably have changed. I sometimes have to load these twice, just so you know. So this is talking about dilations, and in all fairness, rigid motions does not include dilations. I just had nowhere else to put it, so I dropped it into this unit. A dilation is the expansion, the expanding or shrinking of a shape in geometry, and that's actually the opposite of what a rigid motion is. A rigid motion locks the size of the shape to where it is and does not change it. So I apologize for that. That's a little awkward, but I need to start talking about these, and this is the place where it fits, so sorry about that. So first thing you have to understand is a scale factor, and when we start talking about dilations, we're prepping for similarity in geometry. Sometimes I can show, this is a model helicopter. It's a 1/43rd scale model, and it's been through the I've used it over the years, so it's been through the weeds, through the woods, I guess, and it's not in very good shape. Anyway, this model's 1/43rd of the actual helicopter. It's an Augusta A109, and it's painted in the Coast Guard color scheme, and it's got some cool features like retractable landing gear, like the real model, right? And what a model is a shape that has been reduced by a consistent scale factor. So this thing looks like the real one, just shrunk down, right? That's what a scale factor does for us. A scale factor leads us to have the shape looking like the real one, but smaller or bigger. And so we can scale factor up or we can scale factor down. It's also called a zoom factor. The amount at which a shape is shrunk or enlarged, a scale factor of 1 would be no change in the size, right? I always think of that movie where they had a mini-me, right? Mini-me was a 1/4 scale model of Austin Powers or something to that effect. I probably have that wrong. But Mini-Me was a scale model of the original, right? That's what a scale factor does. If you say it's 25% of the original or 1/4 size of the original, it's a scale factor that's shrinking it down, and that number is the scale factor. So given the following pre-image, and we use pre-images again, just like with rigid motions, and we use image after it's been expanded or shrunk. We start with points on a grid here on a Cartesian coordinate plane. Draw a dilation of rectangle ABCD under the center of dilation point P. So P is the origin. So again, we have a center of dilation with a scale factor of 2. So we're going to double the size of that, right? So what happens? Instead of negative 4, 3, we have negative 8, 6. Our points double. So we went from negative 4, 3, and we went twice as big, so it went to negative 8, 6. See how we multiplied both by 2? We were at negative 7, 3. Then we jumped up and went to negative 14, 6, doubling both because the scale factor is 2. We multiplied it by 2. Right? And this is an expansion, an enlargement, a dilation. So scale factor, we went from rectangle ABCD to rectangle A prime, B prime, C prime, D prime, and it was 2.0. And we can also go the other direction. If we went to the larger one, rectangle A prime, B prime, C prime, D prime, we went down to the smaller or original one and went back to it, we'd be 1/2. So the scale factor works to expand toward the larger, and if you're going from the larger back to the smaller, you have to now shrink it, and shrink it by 1/2. All right. Let's see, scale factor flows. I'm not sure what that is, to be honest with you. Let's see, center of dilation. The starting point of the dilation pre-image is the one before. Image is the one after it has been dilated. Expand is to make larger. Shrink is to make smaller. Proportional is two shapes that are the same and related by a scale factor or zoom factor. In other words, this helicopter is the same shape as the real one. It's just a 1/43rd scale model, and hence I can have it on my desk. I obviously couldn't have the real one on my desk, right? Would not fit. Okay, let's see here. So, and here's sort of the idea. Center of dilation starts here, and as our shape expands out, we are able to draw lines out through the original into the expansion. And it works this way with shrinking too. The shrinking would be in here, closer to the center of dilation. All right. With that said, you're going to copy those notes into your comp book on the correct pages according to the table of contents. And let's go and see what problems they give us. What is the pre-image in relation to dilation? So pre-image is before it is dilated. What is the image? The image is after it is dilated. So very similar to the rigid motions terminology. That's why I drop it into this section on rigid motions. But just so you know, a dilation is not a rigid motion. How is the following notation spoken? A prime. So this is A, put a tick mark on it or an apostrophe, and it becomes A prime. Okay, not A apostrophe. That's not it. That's a mislead. All right? No power 2, no squared. It's A prime. So here's a dilation. Given the following graphic, write a proportion from the dilation. So this is interesting because these shapes are what we call similar or proportional in geometry. And similar is a strange word because we use it in real life to mean things are largely the same. But in geometry it means they're exactly the same as related by a scale factor, right? So if this side is 6, see it here? And now it's 12. What do you think the scale factor is? And first, let's establish which is the pre-image and which is the image. I would say because this is A, B, C, right? I would say that this is probably, do I have a way to know which is which? I mean, I guess I would argue that triangle ABC, because it's, you know, earlier in the alphabet than triangle, let's see, ABC, so we go D, E, F, good. D, E, F. I would argue this is the pre-image, and this is the image. This is where it started with, and this is where it ended up. Are they telling us? Maybe they're telling us. Write a proportion. Well, so I'm not totally sure, but they're kind of asking for a proportion. Let's take 8 over 4. So 8 over 4 looks like this side here, 8 over 4. So if we start with 8 over 4, and then they went to 12, so 12 is here. So we went 8 over 4, 12 over 6. All right, 8 over 4, 12 over 6. And notice that 8 over 4 is 2 and 12 over 6 is 2. Check. And so, by the way, our scale factor has got to be 2 here, right? Let's just check 12 over 6. Can't be this. 16 over 8. No, can't be because we already found it. 8, and it wasn't this one. 8 over 6. Let's see. Where's 8 over 6? 8 over 6 would be 12 over 8. 8 over 6. I'm not sure about this one. Don't like it. 12 over 8. So 12 over 8 would be 6 over 4, not 16 over 4. Gone. So just this one. All right? It says more than one answer may apply, though. Look at 12 over 6 again. 12 over 6 equals... Oh, I would go for this one. This one is okay. Let's do it again. So 12 over 6 is this side to this side, right? Equals 16 over 8. That's a check. We went in the same direction with the same two sides in order. So both these answers. I'm glad I looked at that. They gave me a clue to correct my mistake. So given the following graphic, what is the center of dilation? It's this right here. And it looks like it's on the y-axis. Is this the x-axis right here? So this looks like the x-axis. This looks like the y-axis. So yeah, this is 0, 0. That's the origin. No problem. We're asking us easy questions so far. These can get really complicated, but right now, given the following graphic, what is the center of dilation? 0.0. I mean, that's it. We just, easy as pie. That's the center of dilation because everything expands from there. You guys ever done like a perspective drawing in art? It starts to feel like that a lot, doesn't it? Given the following graphic, what is the center of dilation? Got to be right there in the middle because this thing is expanding up at us, right? It's the same distance here to here proportionally, here to here proportionally, here to here. So, oh, I see. This is a y, and this looks like x. So negative 1, 2, 3, 4, and positive 1. Negative 4, positive 1. Apologize that it's so hard to see. The assessment you take or the practice you take will be on the computer and it'll be easier to see, I hope. Okay. Given the following graphic, what's the center of dilation? So it looks like right here. Honestly, it looks like 0, 0. And how would we check? Can I draw a straight line here, here, through all these corners to the center? Yes. It's the origin, 0, 0, because this is the x, this is the y. All right. Given the following graphic, what is the center of dilation? Well, it looks like a home base plate. And I don't know, yes, this is the origin right here. And it looks like it's being expanded straight up off of that and just being enlarged straight up off of that. So I would go for 0, 0. Right? There's no 0.0 and there's no negative 4, 1. So they're making this obvious for us, the misleads. Shapes that are dilated are. More than one answer may apply. So dilated means, you know, it went from this to this or this to this. I'm not sure which is the pre-image, but one is shrunk, one is enlarged. They are proportional. Yes, they are similar. Students learn that new word. That means proportional in geometry. They are identical? No. They are congruent? No. Congruent means equal in geometry. They're not equal. They're proportional or similar. Okay, I like these two answers. All right, so make sure you're following the title of this so you're watching the right video while doing the right practice set. This is Geometry, Semester 1. It's a unit on rigid motions, and it's 05 lesson Dilations practice. It's on creatormath.com under the Geometry tab. Hope that helps.